Right now, photons that began their journey when the universe was 380,000 years old are arriving at your eyes. They have traveled for 13.8 billion years through expanding space. They have witnessed the formation of the first galaxies, the birth of stars, the death of civilizations you will never know existed. And in the final nanosecond of their incomprehensible journey, they will die on your retina. This is not poetic metaphor. This is physics. Every second, trillions of photons complete impossible journeys and meet their end in your optical nerve. Some began their voyage when Earth was a molten ball of rock. Others departed their stellar birthplaces before the sun ignited. A few, the ancient wanderers that carry the most precious information we possess about cosmic history, have been traveling since before the first stars existed at all. They crossed distances so vast that human language fails to capture the scale. And yet they all share the same fate. Arrival means annihilation. The photon striking your eye right now traveled farther than any human will ever go. It survived odds that would humble the imagination of statisticians. It carried information across cosmic voids where a single atom occupies cubic meters of space. It navigated gravitational fields strong enough to bend space-time itself. It endured the relentless theft of cosmic expansion, which stole its energy with every parsec traversed. And now it ends, not with drama or ceremony, but with a quantum transaction so mundane that physics barely acknowledges it happened. The photon transfers its remaining energy to a rhodopsin molecule in your retina. That molecule changes shape. A neural signal fires. The information the photon carried becomes electrical impulse, then memory, then nothing as you forget what you saw a moment ago. The photon itself simply ceases to exist. This is the fate of all light that travels through the cosmos. Whether it journeys for a microsecond or 13.8 billion years, whether it carries the image of a nearby lamp or the echo of creation itself, every photon's existence terminates in absorption. There is no retirement for electromagnetic radiation. There is no rest. There is only travel until interaction, and interaction means death. What happens to light during those billions of years of transit? The answer reveals truths about the universe more disturbing than any science fiction dystopia. Light does not travel unscathed through cosmic distances. It accumulates damage. It loses energy irreversibly. It becomes corrupted by the very structure of space-time through which it moves. The universe does not preserve information perfectly. It degrades it systematically, continuously, inevitably. If you are ready to discover how the cosmos destroys the messages written in light, how expansion steals energy from every photon that crosses intergalactic space, and why the oldest light we can see will be the last light we ever detect from the early universe, then prepare yourself for a journey through 13.8 billion years of photonic suffering. The story begins not in darkness, but in violence. The birth of light, the first photons 380,000 years after the Big Bang. The universe reached a temperature of approximately 3,000 Kelvin. This threshold seems arbitrary until you understand what happened at that precise moment. Below this temperature, electrons and protons combined to form neutral hydrogen atoms for the first time in cosmic history. Above this temperature, the universe existed as an opaque plasma where photons could not travel more than a few centimeters before colliding with free electrons. The transition from plasma to neutral atoms changed everything. Suddenly, photons could travel freely through space. The universe became transparent. These first free photons, born in the moment of decoupling between matter and radiation, constitute the cosmic microwave background radiation that we detect today. They are the oldest light we can observe, the earliest messengers from the infant universe. But these photons were not born gently. They emerged from a universe 1,100 times smaller than it is today, 1.2 million times denser, and incomprehensibly hotter. The surface of last scattering, the moment when these photons last interacted with matter before beginning their 13.8 billion year journey, resembled a wall of fire surrounding every point in space. Everywhere you looked, in every direction, you would see this glowing surface at 3000 Kelvin, bright orange-red like heated metal. The photons that escaped this primordial fireball carried information encoded in their wavelengths and directions. Tiny temperature variations of 1 part in 100,000 created corresponding variations in photon energy. These minute differences, preserved across billions of years of travel, tell us about the density fluctuations in the early universe that would eventually collapse into galaxies, stars, and planets. But preservation is not the same as perfect retention. These photons have been damaged by their journey in ways that fundamentally limit what we can know about our cosmic origins. What is a photon, really? Before we can understand what happens to light over cosmic timescales, we must confront the deeply strange nature of photons themselves. A photon is not a particle in any intuitive sense. It is not a tiny ball of light flying through space. Nor is it simply a wave, despite behaving like one in many experiments. A photon exists in a quantum superposition of these descriptions, manifesting particle-like or wave-like properties depending on how we choose to observe it. This quantum ambiguity matters for cosmic journeys because it determines how photons interact with the universe they traverse. A photon has no mass, yet carries momentum. It has no charge, yet creates electromagnetic fields. It experiences no time, yet travels through time. From the photon's perspective, if such a thing could be said to exist, the moment of emission and the moment of absorption are simultaneous. The 13.8 billion year journey we observe occupies exactly 0 subjective time for the photon itself. This temporal paradox creates profound implications for information transfer across cosmic distances. When we observe ancient light, we are not seeing events that happened long ago from the photon's frame of reference. We are seeing events that, from the photon's perspective, are happening now. The photon exists in an eternal present, connecting emission and absorption in a timeless quantum thread. Yet this thread is not inviolate. The photon may experience no time, but space-time itself acts upon the photon continuously throughout its journey. Every quantum of distance crossed through expanding space extracts a price. The photon's wavelength stretches. Its energy decreases. The information it carries becomes degraded. A photon is born with a specific energy determined by the temperature and conditions at its source. For visible light, this energy ranges from approximately 1.6 to 3.4 electron volts. For gamma rays from violent cosmic events, energies can exceed millions or billions of electron volts. For radio waves from cold interstellar hydrogen, energies may be merely billionths of an electron volt. This initial energy represents the photon's total capacity to do work, to transfer information, to reveal its source. And from the moment of emission, that energy begins to drain away. The moment of emission, consider the birth of a photon in the core of a star. You are created in violence. 2 hydrogen nuclei collide with such force that they overcome the electromagnetic repulsion that normally keeps protons apart. They fuse, forming helium and releasing energy. That energy becomes you, a packet of electromagnetic radiation with no mass, no charge, no allegiance to anything except the speed limit of the universe. But you are not free. You emerge into a hellscape of dense plasma where free electrons fill every cubic centimeter. Your first journey covers perhaps 1 millimeter before an electron scatters you in a random direction. You travel another millimeter, another scattering, another random direction. This process repeats trillions of times. In the sun's core, the density of matter reaches 150,000 kilograms per cubic meter, roughly 150 times the density of water. The temperature exceeds 15 million Kelvin. In this environment, a photon's path resembles a drunkard's walk, zigging and zagging in random directions determined by quantum probability. The photon makes no net progress toward the surface despite moving at the speed of light between collisions. Calculations show that a photon born in the sun's core requires approximately 100,000 to 200,000 years to random walk its way to the surface. The distance from core to surface measures only 700,000 kilometers, a distance light crosses in 2.3 seconds through empty space. But the sun's interior is not empty space. It is a plasma prison where photons serve 100,000-year sentences before parole. During this imprisonment, the photon's energy changes continuously. High-energy gamma rays emitted by fusion reactions scatter off electrons, losing energy with each interaction. The energetic gamma ray becomes an X-ray. The X-ray becomes ultraviolet. The ultraviolet becomes visible light. By the time a photon reaches the solar surface, it has been downgraded from fusion-born gamma radiation to the yellow-white glow we associate with our sun. This energy degradation is permanent. The photon cannot regain what it lost. The information about its origin as a gamma ray has been erased by countless scattering events. When the photon finally escapes into space, it carries no memory of its birth energy, only its current diminished state. And its journey of degradation has only begun. Escaping the star, the transition from stellar surface to interstellar space marks the photon's first taste of freedom. For the first time since its creation, the photon can travel without immediate obstruction. The density drops from millions of particles per cubic centimeter to a few dozen. The mean free path, the average distance between interactions, jumps from millimeters to light years or more. The photon accelerates to its natural velocity of 299,792,458 meters per second in the first instant of freedom. This speed is not fast because the photon tries hard. It is not the result of acceleration from zero. The photon simply is moving at light speed the moment it exists in a region where propagation is possible. There is no gradual speeding up, no building of momentum. Photons exist only at light speed or not at all. From the stellar surface, the photon races outward. If aimed toward Earth, and if the star happens to be our sun, the journey takes approximately 8 minutes and 20 seconds. This duration seems almost instantaneous compared to the 100,000 years spent escaping the stellar interior. But during these 8 minutes, something crucial happens that will determine the photon's fate over cosmic timescales. The photon's wavelength becomes fixed. Within the star, continuous scattering allowed the photon's wavelength to shift with each interaction. But in the near vacuum of space, the photon's electromagnetic wave propagates without interruption. The wavelength at emission determines the wavelength throughout the journey, at least in the photon's local reference frame. This wavelength encodes information about the photon's energy, which encodes information about the temperature and composition of the stellar surface that emitted it. Spectroscopy, the science of analyzing light's wavelength distribution, allows us to determine stellar temperatures, chemical compositions, velocities, and magnetic field strengths entirely from the wavelengths of emitted photons. This works because atoms absorb and emit light at characteristic wavelengths determined by quantum mechanics. Hydrogen absorbs specific wavelengths. Helium absorbs different wavelengths. Iron, calcium, sodium, all elements leave distinctive fingerprints in stellar spectra. These fingerprints persist across cosmic distances, allowing us to analyze stars thousands or millions of light years away. At least, they persist if nothing corrupts the photons during their journey. And here we encounter the first of many mechanisms by which cosmic travel damages light. The stellar exodus continues once free of the star. The photon enters a new phase of existence. No longer buffeted by electrons every millimeter, no longer having its direction randomized billions of times, the photon can finally travel in a straight line. Or more precisely, it can follow a geodesic through space-time, the straightest possible path in whatever curved geometry it happens to traverse. For photons traveling between stars within a galaxy, this journey might span a few light years to a few thousand light years. For photons crossing intergalactic space, the distances stretch to millions or billions of light years. And every meter of that journey presents opportunities for corruption, destruction, or transformation. The first hazard is the simplest. The photon might simply hit something. Despite the common description of space as empty, it is not a perfect vacuum. Atoms, molecules, dust grains, and larger debris populate every cubic meter of supposedly empty space. The density varies enormously depending on location, from perhaps 1 million particles per cubic centimeter in the densest molecular clouds to 1 particle per cubic meter in intergalactic voids. But nowhere is truly empty. When a photon encounters a dust grain comparable in size to its wavelength, several outcomes are possible. The photon might be absorbed completely, its energy converted to heat in the grain. The photon might be scattered, changing direction while retaining most of its energy. The photon might be absorbed and re-emitted at a different wavelength, its original information partially destroyed. None of these outcomes preserves the photon's original state. Absorption means death. Scattering means misdirection, the photon no longer heading toward whatever destination it might have reached. Absorption and re-emission means transformation, a new photon created from the ashes of the old, carrying degraded information about the original source. For visible light crossing the dusty disk of our galaxy, absorption and scattering combine to create extinction, a dimming that can reach factors of 100 or 1,000 for sightlines passing through dense molecular clouds. Blue light suffers more extinction than red light, creating the interstellar reddening that makes distant stars appear redder than they actually are. This reddening is not merely an inconvenience that must be corrected in astronomical observations. It represents real information loss. The blue photons that were absorbed or scattered away carried information about their stellar sources, information that is now lost forever. We can infer what the star should look like based on the red light that survived, but the actual blue light is gone, and with it, the direct information it carried. The photons that do survive the journey through interstellar dust are not pristine. They have been winnowed by wavelength-dependent extinction. They are the survivors of a selection process that preferentially destroyed their bluer companions. The light we receive is biased toward longer wavelengths, not because stars preferentially emit red light, but because red light preferentially survives the journey. This survivorship bias affects every observation we make of distant objects. We are not seeing the universe as it actually is. We are seeing the universe as filtered through trillions upon trillions of absorption and scattering events that preferentially remove certain wavelengths while allowing others to pass. The cosmic landscape we observe is distorted by the journey light must make to reach us. And dust is only the beginning. The corruption runs deeper, woven into the very fabric of expanding space-time itself. Space is not empty. This statement seems obvious, yet the implications remain underappreciated by most people who imagine interstellar space as a perfect vacuum where photons glide effortlessly across light years without encountering any obstacles. The reality is more hostile. The interstellar medium, the space between stars within a galaxy, contains approximately 1 atom per cubic centimeter on average. This seems sparse compared to Earth's atmosphere, which contains roughly 10 to the power of 19 molecules per cubic centimeter. But across light years of travel, even this rarefied medium presents formidable obstacles. Interstellar dust, tiny grains of carbon, silicon, and other elements ejected from dying stars, populates the space between stellar systems. These grains measure typically 0.1 to 1 micrometer in diameter, comparable to the wavelength of visible light. When a photon encounters a dust grain of similar size to its wavelength, several things can happen, none of them good for the photon. First, the photon may be absorbed entirely. The grain's electrons absorb the photon's energy, briefly raising the grain's temperature by an infinitesimal amount. The photon ceases to exist. Its journey ends after perhaps a few thousand years of travel instead of the billions it might have achieved. The information it carried is lost forever, converted to heat in a speck of cosmic debris. Second, the photon may be scattered. The grain's electric field deflects the photon in a new direction, often with a slight energy loss. The photon continues traveling, but no longer heads toward its original destination. If that destination happened to be Earth, we will never detect this photon. It has been removed from our observational universe by random encounter with dust. Third, the photon may be absorbed and re-emitted at a longer wavelength. The grain absorbs the visible light photon and re-emits the energy as infrared radiation. The information about the photon's original source has been partially destroyed. An astronomer detecting the infrared emission will see the dust grain, not the star that originally emitted the photon. Calculations of dust extinction show that visible light dims by approximately 1 magnitude per kiloparsec of travel through typical interstellar medium. 1 kiloparsec equals 3,260 light years. 1 magnitude of dimming means the light appears 2.512 times fainter. Travel through 10 kiloparsecs of dusty space, and visible light becomes 2.512 carat 10 equals 9,900 times dimmer than when emitted. This extinction is wavelength dependent. Blue light, with its shorter wavelength, scatters more efficiently than red light. This is why distant stars appear redder than nearby stars of the same temperature. The blue photons have been preferentially scattered away by dust, leaving the red photons to complete the journey. Astronomers call this interstellar reddening, and it must be corrected for when analyzing distant objects. But dust is not the only obstacle. Interstellar gas, primarily hydrogen and helium, also interacts with photons. Neutral hydrogen absorbs ultraviolet light at specific wavelengths corresponding to electronic transitions in the hydrogen atom. The Lyman series of absorption lines, particularly Lyman alpha at 121.6 nanometers, efficiently removes UV photons from starlight crossing interstellar space. This means that the ultraviolet portion of stellar spectra has been corrupted before the light reaches us. We cannot directly observe the UV emission from distant stars. We see only the wavelengths that survive the journey, the ones that happen not to match hydrogen's absorption frequencies. The information loss is permanent and systematic. Every class of wavelength faces some absorption mechanism. Every photon runs a gauntlet of matter interactions that preferentially destroy certain wavelengths while allowing others to pass. The light that reaches our telescopes is not representative of what the star emitted. It is the survivorship-biased remnant, the wavelengths lucky or resilient enough to complete the journey. The first redshift. Now we must confront the mechanism that dominates all others in determining the fate of ancient light, cosmological redshift. This effect, distinct from the Doppler shift caused by motion through space, arises from the expansion of space itself, and it destroys photon energy with perfect efficiency across billions of years. When astronomers measure the distance to far galaxies, they observe a consistent pattern. The light from these galaxies has been shifted toward longer wavelengths, toward the red end of the spectrum. Spectral lines that should appear in the ultraviolet have moved into the visible range. Visible lines have shifted to infrared. Infrared lines have moved to radio wavelengths. This redshift correlates perfectly with distance. Nearby galaxies show small redshift. Distant galaxies show large redshift. The most distant observable galaxies show redshifts so extreme that their ultraviolet emission arrives as infrared radiation. The relationship between redshift and distance follows a simple formula discovered by Edwin Hubble in 1929. Velocity equals the Hubble constant times distance. But this velocity is not motion through space. Galaxies are not flying away from us through a static universe. Space itself is expanding, carrying the galaxies along like raisins in rising bread dough. The expansion stretches the fabric of space-time, and as that fabric stretches, photons traveling through it also stretch. A photon emitted with a wavelength of 500 nanometers, green visible light, from a galaxy now 10 billion light-years distant has been traveling for approximately 10 billion years. During that journey, the universe expanded by a factor of approximately 1.8. The space between emission point and reception point is now 1.8 times larger than when the photon was emitted, and the photon's wavelength has stretched by the same factor. That green photon at 500 nanometers arrives with a wavelength of 900 nanometers, deep in the infrared. It is no longer visible to human eyes. Its energy has decreased by a factor of 1.8. The photon that could have excited a green-sensitive cone cell in your retina now lacks sufficient energy to trigger any visible light receptor. It has been demoted from the visible spectrum to the invisible. This energy loss is not compensated by any mechanism. The photon simply has less energy upon arrival than at emission. The missing energy has not been transferred to any other particle or field. It has simply been diluted by cosmic expansion, spread thinner across more space. Where did the energy go? This question troubled physicists for decades after redshift was discovered. Energy conservation, one of the most fundamental principles in physics, seemed to be violated by cosmic expansion. Photons lose energy, but nothing gains it. The books do not balance. The resolution lies in understanding that energy conservation applies to closed systems, and the expanding universe is not a closed system. General relativity, the theory governing cosmic expansion, does not require energy conservation in expanding space-time. The cosmological expansion can create or destroy energy without violating any fundamental law. This resolution satisfies the equations, but should horrify anyone who cares about information preservation. The universe is systematically destroying photon energy across cosmic time. The effect is small for nearby sources, but becomes catastrophic for the most distant light. Quantifying the theft, astronomers measure redshift using the variable z, defined as the change in wavelength divided by the original wavelength. A photon emitted at 500 nanometers and detected at 600 nanometers has a redshift of z equals open parenthesis 600 minus 500 close parenthesis divided by 500 is equal to 0.2. The relationship between redshift and energy loss is direct and unforgiving. A photon's energy is inversely proportional to its wavelength. Double the wavelength and you have the energy. Triple the wavelength and the energy drops to 1/3. The energy of a detected photon equals its emission energy divided by 1 plus z. Add z equals 1, corresponding to galaxies roughly 8 billion light-years distant. Photons lose half their energy during travel. A gamma ray emitted at 1 million electron volts arrives as a gamma ray of 500,000 electron volts. Visible green light arrives as near-infrared. Near-infrared arrives as thermal infrared. Add z equals 2, corresponding to approximately 10 billion light-years. photons lose two-thirds of their energy. Only one-third of the original energy remains. At z equals 6, the approximate distance to the earliest galaxies we can observe, photons lose 86% of their energy. Only 14% remains. At z equals 10, marking some of the most distant objects ever detected, photons arrive with only 9% of their birth energy. At z equals 1100, the redshift of the cosmic microwave background radiation, photons have lost 99.91% of their original energy. They arrive as feeble whispers of their former selves. These are not engineering problems that better technology might solve. These are geometrical facts about expanding spacetime. Every photon crossing cosmic distances pays this tax. The universe collects its toll automatically, continuously, without exception. Consider what this means for the information content of ancient light. Information transmission requires energy. Shannon's equations from information theory prove that the maximum information content of a signal is proportional to its energy. A photon with half the energy carries, at most, half the information. The photons from z equals 6 galaxies, those earliest stellar nurseries formed when the universe was less than 1 billion years old, arrive carrying only 14% of their original information capacity. 86% has been erased by cosmic expansion. We are reading messages written 13 billion years ago where 86% of the words have been redacted by geometry. The cosmic microwave background photons have lost 99.91% of their information capacity. These are not pristine signals from the early universe. They are degraded remnants, shadows of the original radiation field that existed at the surface of last scattering. This is not measurement error or instrumental limitation. This is fundamental information destruction built into the structure of an expanding universe. And it gets worse. What expansion does to light the stretching of spacetime? To understand how expansion damages photons requires understanding what expansion actually means at the level of electromagnetic waves. A photon is not a particle with a fixed size that stretches like a rubber band. A photon is a quantized oscillation of the electromagnetic field, a wave packet that propagates through space. When space expands, the underlying electromagnetic field expands with it. The wavelength of a photon is not an independent property that the photon carries. It is a property of the field configuration that represents the photon. Expand the space, and the wavelength increases automatically. Imagine marking 2 points on a rubber sheet 1 centimeter apart. Draw a sine wave between these points with a wavelength of 1 millimeter, creating 10 complete oscillations across the centimeter distance. Now stretch the rubber sheet uniformly until the 2 marked points are 2 centimeters apart. The sine wave has also stretched. Its wavelength is now 2 millimeters. The number of oscillations between the marked points remains 10, but each oscillation occupies twice the space. This is precisely what happens to photons in expanding space. The photon's frequency, the number of oscillations per second, decreases proportionally. Frequency equals the speed of light divided by wavelength. Double the wavelength and you have the frequency. The photon that oscillated 600 trillion times per second when emitted as green light now oscillates only 300 trillion times per second, corresponding to near-infrared radiation. And energy is proportional to frequency. Have the frequency and you have the energy. The mechanism of energy loss is now clear. Expansion stretches the photon's wavelength, decreasing its frequency, which directly decreases its energy. This process operates continuously throughout the photon's journey. For nearby sources, the effect is negligible. A photon from Proxima Centauri, for 0.24 light-years away, suffers cosmological redshift of approximately z equals 0.00001. The wavelength change is 1 part in 10 billion, utterly unmeasurable with any existing technology. The energy loss is similarly infinitesimal. For sources at cosmological distances, the effect dominates all others. A photon from a galaxy at z equals 6 has had its wavelength multiplied by a factor of 7. A 100 nanometer ultraviolet photon arrives as a 700 nanometer red photon. The energy has dropped to 1/7 of the original value. The photon experienced no discrete event that stole its energy. It was not scattered by a particle or absorbed by a dust grain. The photon simply traveled through expanding space, and expansion continuously diluted its energy throughout the journey. This is why cosmological redshift differs fundamentally from Doppler shift. Doppler shift occurs when a source moves through space away from an observer. The photon is emitted with a specific wavelength in the source's reference frame, and geometric effects cause the observer to measure a different wavelength. But the photon itself has not changed. An observer in the source's reference frame would still measure the original wavelength. Cosmological redshift changes the photon itself. Every observer, regardless of motion, would agree that the photon's wavelength has increased during transit through expanding space. The photon that arrives is not the same as the photon that departed. It has been transformed by geometry. Energy loss is permanent. The energy a photon loses to cosmological redshift does not merely relocate elsewhere. It does not heat the intergalactic medium. It does not get absorbed by dark matter. It simply ceases to exist as available energy within the universe's inventory. This statement seems to violate energy conservation, one of the most sacred principles in physics. The first law of thermodynamics states that energy cannot be created or destroyed, only converted between forms. How can photons lose energy with nothing gaining it? The resolution requires understanding that energy conservation is not a universal law. It is a consequence of time translation symmetry, the property that physical laws do not change over time. Emmy Noether proved in 1915 that every symmetry of nature corresponds to a conservation law. Time translation symmetry yields energy conservation. Spatial translation symmetry yields momentum conservation. Rotational symmetry yields angular momentum conservation. But the expanding universe is not time translation symmetric. The physical conditions today differ from conditions a billion years ago and will differ from conditions a billion years hence. The expansion rate changes. The density changes. The temperature changes. The laws of physics remain the same, but the universe's configuration evolves. Without time translation symmetry, energy conservation has no fundamental basis. General relativity, the theory that describes cosmic expansion, does not require or enforce energy conservation in expanding spacetime. Energy can be created or destroyed by the geometric properties of spacetime itself. This resolution satisfies the mathematics, but offers no comfort regarding information preservation. The energy that photons lose to redshift is genuinely gone from the accessible universe. It has been erased by geometry. And since information transmission requires energy, the lost energy represents lost information. Consider a photon from the cosmic microwave background, emitted at z equals 1100. This photon began its journey with a wavelength of approximately 2 micrometers in the near-infrared. The emission temperature of 3000 Kelvin produced photons with energies following a blackbody spectrum centered at this wavelength. After 13.8 billion years of travel through expanding space, this photon arrives with a wavelength of approximately 2 millimeters, shifted all the way into the microwave portion of the spectrum. Its energy has decreased by a factor of 1100. It now carries less than 0.1% of its original energy. The information this photon can convey has been similarly decimated. Where it once encoded details about temperature fluctuations at the surface of last scattering with high precision, it now carries only gross statistical information. The fine details have been erased by the 1100-fold reduction in signal strength. And this is the best-case scenario. These are photons that successfully completed their 13.8 billion-year journey. Many others did not survive. The observable universe shrinks. The expansion of the universe is not constant. For most of cosmic history, gravity slowed the expansion rate, fighting against the initial outward impulse from the Big Bang. If this pattern had continued indefinitely, expansion would eventually halt and reverse, leading to a big crunch where all matter collapses back into a singularity. But observations made in 1998 revealed something unexpected. The expansion rate is not slowing. It is accelerating. Distant supernovae appear dimmer than they should if expansion were decelerating, indicating that space is stretching faster now than in the past. This accelerating expansion is attributed to dark energy, a mysterious component comprising approximately 68% of the universe's total energy content. Dark energy behaves like a cosmological constant, exerting negative pressure that drives expansion faster over time. For photons traveling across cosmic distances, accelerating expansion creates a nightmare scenario. Not only does expansion redshift photons continuously during their journey, but the redshift rate increases as the photon travels. A photon emitted today from a distant galaxy faces stronger expansion during its journey than a photon emitted in the past. This creates an event horizon in space-time, a boundary beyond which light can never reach us regardless of how long we wait. Photons emitted beyond this horizon face expansion so rapid that they make no net progress toward Earth. They travel at light speed toward us, but the space between emission point and Earth expands faster than the photon can cross it. The current cosmological event horizon sits at approximately 16 billion light-years from Earth in moving coordinates. Galaxies beyond this distance cannot send us any signals emitted today. Their light will never arrive, even if we wait trillions of years. More disturbing, this horizon is shrinking. As acceleration continues, the maximum distance from which light can reach us decreases with time. Galaxies currently visible will cross beyond the event horizon in the future. Their light will continue arriving for a while, carrying information about their past, but eventually even this will cease. The galaxies will fade from view not because they stopped emitting light, but because cosmic geometry has severed all connection between them and us. On timescales of trillions of years, this process isolates local groups of gravitationally bound galaxies from all external contact. Future observers in the merged Milky Way Andromeda galaxy will see no other galaxies whatsoever. The cosmic microwave background will have redshifted into undetectability. Every observational signature of the Big Bang will have been erased. Future observers might never discover that other galaxies exist. They might develop cosmological theories from first principles and conclude that their single galaxy represents the entire universe. They would be wrong, but they would have no way to know it. The evidence would have been destroyed by cosmic expansion. We are living in a privileged era where evidence of cosmic history remains accessible. But that window is closing. Every year, some photons complete their final journey from beyond the shrinking horizon. Every year, some galaxies transmit their last signals that will ever reach us. The observable universe is contracting not in size, but in content, as expansion erases more distant regions from observability. This is the context in which ancient photons must be understood. They are not merely old. They are among the last messengers from cosmic distances that will soon fall beyond any possibility of observation. The information they carry will be lost forever when the last photon from those sources arrives and dies. The heat death echo the second law of thermodynamics states that entropy, the measure of disorder or randomness, always increases in closed systems. The universe as a whole constitutes the ultimate closed system, bounded only by the limits of space-time itself. Therefore, cosmic entropy must increase relentlessly, inexorably, toward a maximum value. This maximum entropy state is called heat death. In this configuration, all energy has been evenly distributed throughout all available space. No temperature gradients exist. No concentration of energy persists. The universe reaches perfect thermodynamic equilibrium at an extremely low but non-zero temperature. In a heat-death universe, no stars burn because all nuclear fuel has been exhausted. No planets orbit because tidal forces have gradually robbed orbital energy over timescales exceeding trillions of years. No life exists because life requires energy gradients to power metabolism. The universe becomes a cold, dark, perfectly uniform expanse of extremely dilute radiation and matter. Current cosmological models suggest heat death occurs on timescales of 10 to the power of 100 years or longer, so far in the future that human language struggles to capture the duration. Yet the process has already begun. Every photon that gets redshifted by cosmic expansion contributes to heat death. Every star that burns hydrogen into helium increases entropy. Every galaxy that radiates energy into intergalactic space moves the cosmos incrementally toward equilibrium. The photons traveling through space right now are not innocent messengers preserving information across cosmic distances. They are participants in the heat death of the universe. Each photon carries energy away from concentrated sources like stars and galaxies, radiating it into the growing volume of empty space. Each photon that gets redshifted loses energy that will never again be available to do useful work. This is the ultimate fate of all light. Not just absorption at a detector or scattering by dust, but contribution to the universal slide toward maximum entropy. The information photons carry today will eventually be degraded beyond recovery by the same expansion that currently redshifts distant galaxies. On timescales of billions of years, even the cosmic microwave background will redshift into undetectability. The photons will still exist, technically, but their wavelengths will stretch to meters, then kilometers, then light years. Their energy will approach zero asymptotically. They will become indistinguishable from the vacuum itself. At that point, the information about the early universe encoded in CMB photons will have been effectively destroyed. Future observers, if any exist, will have no way to detect these ultra-redshifted photons. The evidence of cosmic history will have been erased by geometry. This is not a failure of technology or a limitation of measuring instruments. This is thermodynamic inevitability. Information degrades. Energy dissipates. Entropy increases. The universe forgets its own history as expansion dilutes all signals below detectability. And we are watching it happen in real time. While cosmological redshift dominates energy loss over billions of light years, other mechanisms damage photons over shorter distances. Interstellar dust creates the first major obstacle for light attempting to cross a galaxy. Dust grains form in the atmospheres of dying stars, particularly asymptotic giant branch stars that shed their outer layers near the end of their lives. These grains consist of silicates, graphite, and more exotic materials like silicon carbide and polycyclic aromatic hydrocarbons. They measure typically 0.1 to 1 micrometer in diameter, comparable to the wavelength of visible light. When a photon encounters a dust grain of similar size to its wavelength, the photon may be absorbed, scattered, or both. The probability of each outcome depends on the grain's composition, size, and shape, as well as the photon's wavelength. Absorption converts the photon's energy into heat within the dust grain. The grain's temperature increases infinitesimally. The photon ceases to exist. If this occurs, the photon's journey has ended prematurely. The information it carried about its source is lost. Scattering redirects the photon without necessarily destroying it. The grain's electric field interacts with the photon's electromagnetic wave, causing it to propagate in a new direction. From an observer's perspective on Earth, the photon has been removed from the light beam because it no longer travels toward us. Another observer in a different direction might detect it. But scattering is not a clean process that preserves photon properties perfectly. Each scattering event may shift the photon's wavelength slightly. Multiple scatterings accumulate these shifts, gradually changing the photon's color even if it somehow eventually reaches its original destination. The combined effect of absorption and scattering is called extinction. Astronomers measure extinction in magnitudes, where one magnitude of extinction makes an object appear 2.512 times dimmer. Extinction increases with distance through dusty regions and varies strongly with wavelength. Blue light suffers more extinction than red light because shorter wavelengths interact more strongly with dust grains. This wavelength dependence follows approximately a power law. Extinction is proportional to wavelength raised to the power of -1 to -1.5, depending on grain size distribution. This creates interstellar reddening. Stars appear redder than their actual temperatures would suggest because blue photons have been preferentially removed by dust. An astronomer observing a distant star must correct for this reddening to infer the star's true temperature and other properties. The correction is not trivial. Extinction can reach several magnitudes even within our galaxy for sight lines through the galactic plane. A star suffering 5 magnitudes of visual extinction appears 100 times dimmer than it would without dust. If that extinction is not properly accounted for, the star's distance, luminosity, and other properties will be grossly miscalculated. Worse, extinction is not uniform. Dense molecular clouds can create 20+ magnitudes of extinction, rendering anything behind them completely invisible at optical wavelengths. The Milky Way's core, lying approximately 26,000 light-years away in the constellation Sagittarius, cannot be observed in visible light because intervening dust blocks all optical photons. Infrared observations partially circumvent this problem because longer wavelengths suffer less extinction. A dust cloud that produces 20 magnitudes of extinction in blue light might produce only 2 magnitudes in infrared. This allows infrared telescopes to peer through dusty regions that are opaque to optical light. But infrared photons face their own challenges. They must compete with thermal emission from the dust itself. A dust grain heated to 30 Kelvin by starlight emits primarily in the far infrared, creating a background glow that can overwhelm the signals we wish to detect. Subtracting this foreground emission introduces noise and uncertainty that degrades the information in detected photons. No wavelength escapes dust effects entirely. Submillimeter and radio waves can penetrate the densest clouds, but even these long wavelengths experience some absorption and scattering. Across all wavelengths, dust damages or destroys a significant fraction of photons attempting to cross galactic distances. For extragalactic light crossing intergalactic space, dust is less problematic because the intergalactic medium contains minimal dust content. But within galaxies, including our own, dust extinction shapes what we can observe and what remains forever hidden. Gravitational lensing gravity bends light. This prediction of general relativity, confirmed spectacularly during the 1919 solar eclipse, means that photons traveling through curved spacetime do not follow straight lines. They follow geodesics, the straightest possible paths in curved geometry, which appear curved to external observers. For photons crossing cosmic distances, gravitational lensing creates both opportunities and problems. On one hand, Massive objects like galaxy clusters can act as natural telescopes, magnifying background objects and allowing us to see farther than would otherwise be possible. On the other hand, lensing distorts images, creates multiple copies of single objects, and introduces time delays that complicate interpretation. Strong gravitational lensing occurs when a massive object lies nearly along the line of sight between us and a background source. The foreground mass, typically a galaxy or galaxy cluster containing trillions of solar masses, bends light from the background source around itself. If the alignment is precise, this creates an Einstein ring, a circular arc of light surrounding the lensing mass. More commonly, the alignment is imperfect, creating multiple images of the background source arrayed around the lensing mass. The most spectacular examples show 4 or more images of a single distant quasar, each taking a slightly different path around the foreground galaxy. These multiple images do not arrive simultaneously. Light traveling different paths through curved space-time experiences different travel times. One path might be slightly shorter but pass through deeper gravitational potential where time runs slower. Another path might be longer but avoid strong gravitational fields. The result is that photons from a single event at the source arrive at Earth over periods ranging from days to years. When a distant quasar varies in brightness due to instabilities in its accretion disk, we see that variation occur in one lensed image, then weeks or months later in another image. The time delay depends on the mass distribution of the lensing object and the geometry of the system. This time delay creates problems for interpreting rapid variations in distant sources. Imagine a supernova exploding in a lensed galaxy. The explosion brightens over days, then dims over weeks. But we observe this light curve multiple times, offset by the lensing time delays, potentially creating confusion about whether we are observing one supernova or several. Weak gravitational lensing produces more subtle distortions. Rather than creating multiple images, weak lensing slightly stretches or shears images of background galaxies. The effect is small for any individual galaxy, but statistical analysis of thousands of background galaxies reveals the gravitational influence of foreground structure. This cosmic shear allows astronomers to map dark matter distribution across the universe by observing how it lenses background light. The technique works beautifully for this purpose, but it means that essentially all photons from distant sources have been gravitationally distorted to some degree. The images we observe are not pristine representations of distant objects. They are warped by intervening mass. Galaxies appear elongated in directions determined by foreground dark matter. Clusters appear magnified or demagnified depending on the lensing configuration. Even the cosmic microwave background shows gravitational lensing signatures from large-scale structure. For cosmology, this lensing can be corrected statistically. But for individual photons, the information has been corrupted. A photon arrives from a slightly different direction than it would have in the absence of lensing. Its path was bent by dark matter we cannot directly observe. The information it carries about its source has been mixed with information about the matter distribution it traversed. This mixing is irreversible. We cannot perfectly unscramble the lensing effects to recover the original unlensed image. We can make statistical corrections that work well for large samples, but individual photons have been permanently altered by their gravitational interactions. Quantum foam speculative general relativity and quantum mechanics, the two foundational theories of modern physics, are famously incompatible at the smallest scales. General relativity treats space-time as a smooth continuum. Quantum mechanics requires that everything, ultimately, is quantized and probabilistic. The quantum nature of space-time itself remains unknown because we lack a theory of quantum gravity. But several approaches to quantum gravity suggest that space-time, at scales near the Planck length of 10 to the power of -35 meters, might not be smooth at all. It might fluctuate wildly, with geometry bubbling and churning in a foam-like structure. If quantum foam exists, what happens to photons traveling through it? A photon's electromagnetic wave oscillates at wavelengths ranging from nanometers to meters, vastly larger than the Planck scale. One might expect that quantum foam, if it exists at all, would be irrelevant for electromagnetic propagation. But photons traveling cosmic distances traverse tremendous amounts of space. Even infinitesimal effects per unit distance could accumulate to observable consequences over billions of light years. Some theoretical models suggest quantum foam might cause very slight dispersion, meaning photons of different wavelengths travel at slightly different speeds. This would violate the principle that the speed of light is constant for all wavelengths, a cornerstone of special relativity. Tests of this possibility use gamma-ray bursts, cosmic explosions that produce photons with energies ranging from visible light to multi-GeV gamma rays. If quantum foam causes dispersion, high-energy photons should arrive at Earth slightly delayed or advanced compared to low-energy photons, even though they were emitted simultaneously. Current observations find no evidence for such dispersion down to extremely precise limits. Photons from gamma-ray bursts billions of light years away arrive with timing independent of energy, suggesting that if quantum foam exists, it does not cause measurable dispersion effects at current sensitivity levels. But absence of evidence is not evidence of absence. Quantum foam might exist below current detectability thresholds. It might affect photons in ways that do not produce wavelength-dependent speeds. It might couple to photons through mechanisms we have not yet imagined. The point is that we do not know what happens to photons at the quantum level during cosmic journeys. We can measure what emerges, but the complete history of quantum interactions during transit remains unknown and perhaps unknowable. If space-time itself fluctuates quantum mechanically, then every photon's path is probabilistic at the finest scales. The photon that arrives is not the inevitable result of classical propagation, but one possible outcome from a quantum superposition of paths. The information about which specific path was taken has been lost to decoherence. This is admittedly speculative, based on theories that remain unproven and possibly unprovable with current technology. But it illustrates an important point. Our understanding of what happens to photons during cosmic journeys is incomplete. We observe emission and absorption. Everything in between is inferred from theory, and the theory itself has gaps. Collisions with other particles space is not perfectly empty. Even intergalactic voids, the most empty regions in the universe, contain approximately 0.1 atoms per cubic meter. Over cosmic distances, photons eventually encounter matter. Most interactions are benign. A photon passing near an atom or electron may experience slight deflection without absorption, causing negligible changes to the photon's properties. But some interactions destroy or transform the photon. High-energy gamma rays can collide with lower-energy photons to produce electron-positron pairs. This process, called pair production, requires the combined energy of both photons to exceed twice the electron rest mass energy, approximately 1.02 MeV. Above this threshold, two photons can annihilate, creating matter from pure energy. This process limits how far ultra-high energy gamma rays can travel through space. The universe contains a background of optical and infrared photons produced by stars and galaxies throughout cosmic history. This extragalactic background light fills space uniformly at a density of approximately 1 photon per cubic centimeter. A TeV energy gamma ray photon traveling through this background has a high probability of colliding with a background photon and producing an electron-positron pair. Calculations show that TeV gamma rays can travel only a few hundred million light years before being absorbed via this process. This creates a gamma ray horizon, analogous to the cosmological event horizon, but caused by physics rather than geometry. We cannot detect TeV gamma rays from sources beyond a few hundred MPC because the photons are destroyed by pair production before reaching Earth. Lower energy photons do not experience pair production because they lack sufficient energy, but they can interact with electrons via Thomson scattering, a process where the photon bounces off a free electron, changing direction and wavelength. In ionized regions, where hydrogen atoms have been split into free protons and electrons, Thomson scattering can significantly alter light. The cosmic microwave background photons last scattered off electrons at the surface of last scattering. Before that moment, photons scattered many times, creating an opaque plasma that light could not traverse. Even today, photons passing through ionized regions experience Thomson scattering. Hot gas in galaxy clusters contains free electrons that scatter SIMB photons, slightly boosting their energy through a process called the Sunyaev-Zeldovich effect. This creates shadows and CMB maps where galaxy clusters reside, as photons gain energy by scattering off hot electrons. For individual photons, scattering represents another mechanism of information corruption. A photon that scatters has been redirected and possibly shifted in wavelength. The information about its original source has been partially erased, replaced by information about the scattering environment. The lesson is that space is not an ideal transmission medium for electromagnetic radiation. It is filled with particles, fields, and structures that interact with light, degrading and corrupting the information photons carry. The perfect vacuum of science fiction does not exist. Real space is messy, and photons bear the scars of their journey through it. The cosmic microwave background, the oldest light we can see. 380,000 years after the Big Bang, the universe cooled below 3,000 Kelvin. At this temperature, electrons and protons combine to form neutral hydrogen atoms. This recombination event fundamentally changed the universe's transparency. Before recombination, the universe existed as an ionized plasma. Free electrons filled space, scattering photons continuously. Light could not travel more than a few centimeters before encountering an electron and scattering in a new direction. The universe was opaque, like being inside a luminous fog where light comes from everywhere, but nothing can be seen clearly at any distance. After recombination, suddenly there were no free electrons. Photons could travel freely across the universe without scattering. The fog cleared. The universe became transparent. The photons that last scattered off electrons at the moment of recombination have been traveling freely ever since. They constitute the cosmic microwave background radiation, the oldest light we can observe. Every point in space was once part of the hot plasma surface that emitted these photons. Looking outward in any direction, we see this surface at a distance determined by how far light could travel in 13.8 billion years. But we do not see the surface as it was at recombination. We see it as it appears now, after 13.8 billion years of cosmic expansion have redshifted the photons from their original wavelengths. At emission, CMB photons formed a blackbody spectrum centered at approximately 2 micrometers wavelength, corresponding to the 3,000 Kelvin temperature of the recombination surface. This is near infrared radiation, invisible to human eyes but detectable as heat. After 13.8 billion years of redshift, these photons now have wavelengths centered around 2 millimeters, shifted by a factor of 1100. The temperature has correspondingly dropped from 3000 Kelvin to 2.725 Kelvin, barely above absolute zero. The CMB now appears as microwave radiation, hence its name. It fills the universe uniformly in all directions with a temperature of 2.725 Kelvin and a nearly perfect blackbody spectrum. This uniformity is extraordinary. Looking at one part of the sky and then a completely different part shows the same temperature to within one part in 100,000. But this near-perfect uniformity itself encodes information. The tiny temperature fluctuations, the one part in 100,000 deviations from average, correspond to density fluctuations in the plasma at the surface of last scattering. Slightly denser regions were slightly hotter. Slightly less dense regions were slightly cooler. These density fluctuations were the seeds from which all cosmic structure grew. Regions that were slightly overdense at recombination attracted more matter gravitationally, becoming more overdense over time. Eventually, these overdensities collapsed into the first stars, galaxies, and galaxy clusters. By measuring CMB temperature fluctuations across the sky, we can map the density field of the universe 380,000 years after the Big Bang. This map reveals the initial conditions from which everything we see today emerged. It contains information about the amount of ordinary matter, and dark energy in the universe. It constrains the rate of cosmic expansion and the geometry of space-time itself. No other observation provides this information. The CMB is the only direct window into the universe's first few 100,000 years. All other observations show the universe at later times after galaxies formed and stars began shining. But the window is closing. What it looked like then, imagine standing at the surface of last scattering, 380,000 years after the Big Bang. You are embedded in a hot plasma at 3,000 Kelvin, glowing orange-red in all directions. The light does not come from distant stars. It comes from the plasma itself, from the thermal emission of free electrons and protons about to combine into neutral atoms. If you could see in all directions simultaneously, you would observe a perfectly uniform glow, the same color and brightness everywhere you looked. There are no stars yet, no galaxies, no structure of any kind visible at this moment. The density variations that will seed galaxy formation are present but utterly invisible to the eye, differing from average by only one part in 100,000. The plasma is not perfectly still. It is ringing with acoustic oscillations, sound waves traveling at a significant fraction of light speed through the hot, dense medium. These oscillations were set up by quantum fluctuations in the earliest moments after the Big Bang, amplified by cosmic inflation into macroscopic density variations. The sound waves created regions of compression and rarefaction, areas slightly denser and slightly less dense than average. In the denser regions, gravity tried to compress matter further. Radiation pressure from the intense photon field resisted this compression. The competition between gravity and radiation pressure created oscillating waves, like the vibrations of a struck drumhead. At recombination, these oscillations were frozen in place. The photons that had been trapped in the plasma suddenly decoupled and streamed freely across the universe. They carried with them an imprint of the density field at that final scattering moment, encoding information about the amplitude and scale of the acoustic oscillations. This information is what we measure today in the CMB temperature fluctuations. The angular scale of hot and cold spots in the CMB corresponds to the wavelength of acoustic oscillations at recombination. The amplitude of temperature fluctuations corresponds to how strongly the plasma was oscillating. From these measurements, cosmologists can infer fundamental parameters of the universe with extraordinary precision. The total energy density, the relative amounts of ordinary matter and dark matter, the rate of expansion, the geometry of space, all are encoded in the pattern of CMB fluctuations. But we can only measure what arrives. And what arrives has been damaged by 13.8 billion years of cosmic expansion. What it looks like now when CMB photons reach our detectors, they carry only a tiny fraction of their birth energy. The 1100-fold redshift has reduced their energy by the same factor. Photons that could have raised material to 3000 Kelvin at emission now contribute only 2.725 Kelvin of equivalent temperature. This energy loss translates directly to information loss. The signal-to-noise ratio of CMB observations is limited by how many photons we can collect. Each photon delivers less energy and therefore less information than it would have at emission. Worse, the signal we wish to measure is extremely faint. The temperature fluctuations that encode information about early universe structure are only microkelvin in amplitude. Measuring temperature differences of 1 part in 100,000 requires detecting billions of photons to achieve sufficient statistical precision. Even with perfect detectors, photon-shot noise creates an irreducible uncertainty. Collecting N photons provides information with uncertainty proportional to 1/sqrt N. To measure a 1 part in 100,000 temperature fluctuation requires collecting at least 10 billion photons from each sky patch being analyzed. The CMB contains only about 400 photons per cubic centimeter on average. A telescope with 1 square meter collecting area pointed at a patch of sky 1 degree across collects CMB photons at a rate of approximately 1 million per second. To gather 10 billion photons requires roughly 3 hours of observation time per sky patch. Mapping the full sky with sufficient sensitivity to measure the faintest fluctuations requires years of observation time with multiple telescopes. Missions like WMAP and Planck spent years collecting CMB data to achieve their final results. And even after years of observation, fundamental limits constrain what can be measured. The CMB photons have scattered off hot electrons in galaxy clusters between recombination and today, a process called secondary anisotropy. This scattering adds noise that obscures the primordial signal. Gravitational lensing by large-scale structure between recombination and observation has distorted the CMB fluctuation pattern, mixing information about different angular scales and complicating interpretation. Foreground emission from our galaxy, from dust, free electrons, and other sources, contaminates the CMB signal. These foregrounds must be carefully subtracted, introducing uncertainty and potential systematic errors. After all corrections and analysis, the information we extract from the CMB is a degraded version of what was available at emission. We learn about the early universe, but with reduced precision and limited resolution. The finest details have been lost to redshift, contamination, and fundamental measurement limitations. The information it carries despite 13.8 billion years of degradation, CMB photons still carry remarkable information. The temperature fluctuation pattern encodes the total energy density of the universe, measured to better than 1% precision. The density of ordinary matter, determined to within a few percent. The density of dark matter, constrained to approximately 10% uncertainty. The amplitude of initial density fluctuations, measured precisely across a range of scales. The spectral index of fluctuations, indicating how fluctuation amplitude varies with scale. The universe's age, determined to within 1% from the CMB data combined with other observations. The Hubble constant, the expansion rate at the present epoch, though with some tension compared to local measurements. The spatial geometry, indicating that space is flat to within measurement precision. This is an extraordinary amount of information to extract from faint microwave radiation filling the sky. The success of CMB cosmology represents one of the great achievements of 20th and 21st century science. But we are nearing the limit of what can be learned from the CMB. Future experiments will improve sensitivity and angular resolution, but they will not fundamentally change what is accessible. The primary fluctuations, the signal from recombination itself, have been measured to near cosmic variance limits. Cosmic variance refers to the fact that we have only one universe to observe. We see only one realization of the random density fluctuations produced in the early universe. We cannot average over multiple universes to reduce statistical uncertainty. This creates a fundamental limit on measurement precision for features at large angular scales. For the largest scale fluctuations, we have already reached cosmic variance limits. Future observations will not significantly improve these measurements because the limitation is not instrumental but fundamental. We have essentially one sample to measure, and we have measured it. The information content of the CMB is finite. It is very large, containing details about the state of the universe at recombination, but it is not infinite. Eventually, we will extract all accessible information, and no further observations will add knowledge. When that point arrives, we will have learned everything the CMB can teach us. The photons will continue arriving, carrying the same information they always have. But we will have already received the message. The subsequent photons will be redundant, repetitive echoes of information we have already decoded. And on cosmological timescales, even these echoes will fade. Every photon's journey ends in absorption. Photons do not decay spontaneously like radioactive atoms. They do not tire and slow down like macroscopic objects subject to friction. A photon in vacuum will propagate forever at light speed unless it encounters matter. But eventually, every photon does encounter matter. The universe is not infinitely transparent. Given enough time and distance, every photon strikes a particle, a grain of dust, a molecule of gas, or arrives at a detector. At that moment, the photon ceases to exist. The absorption process occurs at quantum scales over timescales measured in femtoseconds. The photon's electromagnetic wave interacts with the electric field of electrons in an atom or molecule. If the photon's energy matches an allowed transition in the atom's energy level structure, the atom absorbs the photon completely. The photon's energy transfers to the atom, raising an electron from a lower energy state to a higher one. The electron now occupies an excited state, a quantum configuration with more energy than the ground state. This excited state is typically unstable. Within nanoseconds to milliseconds, the electron drops back to a lower energy level, emitting a new photon in a random direction. The emitted photon is not the same photon that was absorbed. Quantum mechanically, photons are indistinguishable, but we can track energy flow. The original photon was destroyed upon absorption. A new photon was created upon emission. The direction, phase, and possibly wavelength of the new photon differ from the original. From an information perspective, absorption and re-emission scrambles the signal. The original photon carried information about its source encoded in its direction, wavelength, polarization, and arrival time. The re-emitted photon randomizes direction and phase, destroying most of this information. If absorption occurs in your retina, the energy transfers to a rhodopsin molecule rather than being re-emitted. Rhodopsin is a light-sensitive protein that changes shape when it absorbs a photon. This shape change triggers a cascade of biochemical signals that ultimately produce a neural impulse in your optic nerve. The photon's energy becomes the energy of a chemical reaction. The information it carried becomes neural information. Your brain processes this signal, and you perceive light. The photon has served its purpose and been destroyed in the process. For photons absorbed by telescope detectors, the process is similar. CCD sensors convert photon energy to electric charge, creating a digital signal that records the photon's arrival position and time. The photon is destroyed, but its information is preserved in digital form for later analysis. But consider what is lost even in this best-case scenario. The photon's phase information is lost. The exact timing beyond the detector's time resolution is lost. Polarization information may be lost if the detector is not polarization sensitive. Wavelength information is lost unless the detector includes spectroscopic capability. A perfect detector might preserve most of the information a photon carries. But no detector is perfect. Quantum efficiency, the fraction of incident photons actually detected, is always less than 100%. Many photons strike the detector and fail to register, their information lost entirely. Those that are detected have their continuous properties discretized. The position is binned to pixel resolution. The time is binned to clock resolution. Wavelength is binned to spectral channel width. Each discretization loses information about the original photon. The information that survives detection is then subject to processing, analysis, calibration, and error correction, each step potentially introducing further information loss. By the time we publish scientific results based on detected photons, the information has passed through many lossy transformations. We can never recover the complete information the photons originally carried. We can only access the highly processed remnant that survives the detection and analysis chain. And this is for photons that reach detectors at all. The vast majority of photons emitted by stars, galaxies, and other cosmic sources never encounter any detector. They propagate through space until they are absorbed by interstellar dust, gas, or some other random particle. When a photon is absorbed by a dust grain in the interstellar medium, its energy simply heats the grain infinitesimally. The information it carried about its stellar source is lost forever. No one will ever measure that photon. No data will be recorded. The photon's journey was cosmically meaningless. This is the fate of most photons. They travel for thousands or millions or billions of years, crossing distances that dwarf human comprehension, carrying information about their sources across cosmic voids. And then they strike a random atom and vanish, contributing a quantum of heat to a particle that will never be observed by anyone. The final energy transfer when a photon is absorbed, where does its energy go? At the most fundamental level, the photon's energy becomes part of the absorbing particle's internal energy. For a single atom, this means raising an electron to an excited state. For a molecule, it might mean exciting vibrational or rotational modes. For a solid, it might mean creating phonons, quantized lattice vibrations that we perceive macroscopically as heat. The key point is that the photon's electromagnetic energy converts to kinetic energy of particles. The ordered energy of a photon, carrying momentum in a specific direction at a specific wavelength, becomes the disordered energy of thermal motion. This conversion is irreversible. Thermodynamics forbids perfect conversion of heat back into ordered radiation. Some energy can be converted back, as when an excited atom emits a photon, but the emitted photon typically has different properties than the absorbed photon. Direction is randomized. Phase relationships are lost. Coherence is destroyed. From an information-theoretic perspective, absorption increases entropy. The highly ordered state of a propagating electromagnetic wave becomes the disordered state of thermal motion. Information is lost as order becomes disorder. 4 cmb photons absorbed in a detector, the energy transfer is almost comically lopsided. Each 2.7 Kelvin photon carries approximately 0.0002 electron volts of energy. This is roughly 1 billion times less than the energy needed to ionize a hydrogen atom. It is almost nothing. Yet this nothing is detectable. Extraordinarily sensitive detectors cooled to millikelvin temperatures can register individual microwave photons. They do so by using superconducting sensors that change resistance when heated even slightly. The minuscule energy of a single CMB photon suffices to create a measurable signal. But measuring the signal destroys the photon. The energy enters the detector and dissipates as heat. The photon is gone. Its 13.8 billion year journey has ended. The information it carried has been converted to digital data, a string of ones and zeros in a computer's memory. Is this preservation of information or destruction? The answer is both. The specific information about where the photon came from, when it was emitted, and what it encountered along the way has been encoded in digital form. This is preservation. But the photon itself, the physical carrier of that information, has been annihilated. And subtle information encoded in properties that were not measured has been lost forever. The photon's phase, its exact arrival time beyond detector resolution, any correlations with other photons that were not detected, all this is gone. We preserve what we can measure and lose what we cannot. And we can never measure everything about a photon because quantum mechanics forbids perfect measurement of all properties simultaneously. Heisenberg's uncertainty principle ensures that measuring position precisely makes momentum uncertain and vice versa. So even perfect detection destroys some information, and detection is never perfect. Quantum efficiency is less than 1. Noise corrupts signals. Systematic errors introduce artifacts. The information that survives is a pale shadow of what the photon originally carried. Information death information theory, developed by Claude Shannon in the 1940s, quantifies information content mathematically. The information content of a signal is proportional to its entropy, the number of possible states it could occupy. A highly specific signal carries more information than a vague one. A photon carries information in its wavelength, direction, polarization, and arrival time. If each property can be measured to arbitrary precision, the information content is infinite. But quantum mechanics limits precision. There is a minimum uncertainty in any measurement, set by Planck's constant and the duration of the measurement. Taking these limits into account, a photon carries approximately log 2, 1 plus SNR, bits of information per property, where SNR is the signal-to-noise ratio. For a photon detected with SNR of 1000, this is approximately 10 bits per property. With 4 measurable properties, the total information content is approximately 40 bits. 40 bits is not much information. It is less than the information in a single character typed on a keyboard. Yet this is the maximum information content of a single photon under ideal detection conditions. For photons that have been redshifted by factors of thousands, the SNR is much worse. The signal is weaker. Noise dominates. The information content drops accordingly. A CMB photon might carry only a few bits of useful information after 13.8 billion years of redshift and degradation. And this small amount of information is further reduced by absorption. The photon must be detected to extract any information. Detection destroys the photon. We get one chance to measure, and our measurement is imperfect. If we measure wavelength with high precision, we lose information about arrival time. If we measure position accurately, we lose momentum information. We must choose what to measure, accepting that unmeasured properties are lost. After measurement, the photon no longer exists. Its information has been partially transferred to our detectors and partially lost to unmeasurable quantum properties. The photon cannot be measured again. Its information cannot be recovered from the void. This is information death, not gradual degradation, but sudden termination. The photon existed, carrying information across cosmic distances. Now it is gone, and some of its information is gone with it. Multiply this by the trillions upon trillions of photons absorbed by random dust grains, gas molecules, and cosmic debris. Each absorption event is an information death. Information about stellar spectra, galactic structure, cosmic chemical composition, all lost because the photons that carried it were absorbed without being measured. We can only learn what we measure, and we can only measure a tiny fraction of the photons the universe emits. The rest carry information that will never be decoded, dying in random absorption events scattered across cosmic space and time. The universe does not preserve information about its own state perfectly. It leaks information constantly through photon absorption. The past becomes increasingly inaccessible as the photons that could tell us about it are destroyed one by one. Heat death echo on the longest timescales. All photons contribute to the universe's heat death. Heat death, the state of maximum entropy where no energy gradients remain, represents the ultimate fate of cosmic evolution. Every photon emitted by a star carries energy away from the star's concentrated energy reservoir and radiates it into the growing volume of space. This energy dilution is the essence of heat death. Energy spreads from concentrated sources into diffuse background radiation. The CMB itself is already a heat death phenomenon. The hot plasma of the early universe has cooled through expansion, redistributing its energy across ever larger volumes of space. The 3000 Kelvin radiation has become 2.7 Kelvin radiation. Eventually, it will become millikelvin radiation, then microkelvin, asymptotically approaching absolute zero. But it never quite reaches zero. The energy in CMB photons remains in principle, though increasingly diluted and increasingly difficult to access. In the far future, when the last stars have burned out and the last black holes have evaporated, the universe will contain only this ultra-dilute radiation field and dark matter. The photons will still exist, technically, but their wavelengths will have stretched to astronomical lengths. Their energy will have dropped to levels indistinguishable from vacuum fluctuations. They will no longer constitute measurable radiation in any practical sense. At that point, the information the photons carry has been destroyed not by absorption, but by dilution. The signal still exists, but with amplitude below any possible detection threshold. Information that cannot be accessed is, functionally, lost information. This is the ultimate fate of all photons that do not get absorbed first. They redshift into irrelevance, their information diluted beyond recovery. Their energy spreads so thin across space that it might as well not exist. The universe forgets. Expansion erases memory. The photons that carry information about cosmic history are either destroyed by absorption or rendered unreadable by redshift. Either way, the information is lost, and we are watching it happen. Every second, photons from distant galaxies arrive at Earth carrying information that will never be available to future observers. We are living in the brief epoch where this information is accessible. Before us, the universe was opaque. After us, it will have expanded beyond informationally meaningful observation. We are the generation that can read the universe's message written in ancient light. Future generations will inherit only fragments. Eventually, there will be no message left to read at all. The dark photons beyond the event horizon, the cosmological event horizon, defines the boundary beyond which events occurring today can never be observed from Earth. Photons emitted beyond this horizon, currently approximately 16 billion light-years distant in comoving coordinates, are fighting a losing battle against cosmic expansion. These photons travel toward Earth at light speed. But the space between emission point and Earth expands faster than the photons can cross it. The photons make no net progress. They are trapped in an expanding void, racing forward yet falling backward relative to their destination. From the photons' perspective, nothing has changed. They propagate at light speed, as all photons must. The universe looks the same in their reference frame. But from an external observer's perspective, these photons will never complete their journey. They will travel for trillions of years, crossing distances that would make current cosmic distances seem trivial. But they will never arrive. Expansion will always stay ahead of them, adding more distance to cross faster than they can. Cover existing distance. These photons are effectively dead on emission. They carry information that will never be received. They are messages thrown into a void from which no message can escape. The universe has created a boundary in space-time that functions like a black hole event horizon, but inverted. Rather than preventing escape, it prevents arrival. And this horizon is expanding. Galaxies currently within the horizon will cross beyond it in the future as acceleration continues. Their future photons will join the population of dark photons, traveling perpetually without destination. How many photons exist in this state? The answer is difficult to calculate precisely, but the number is surely staggering. Every second, trillions upon trillions of stars and galaxies beyond the event horizon emit photons into space. Every one of these photons is trapped, unable to reach observers in other galaxies that have crossed beyond the horizon. These are not wasted photons from a cosmic perspective because the universe has no goals or purposes. But from an information perspective, this represents the largest information quarantine in existence. Vast amounts of information about galactic structure, stellar populations, chemical evolution, and cosmic history are being generated constantly in regions of space that are causally disconnected from us. We will never know what is happening in those regions. We cannot send signals there. They cannot send signals here. The information barrier is absolute and permanent, enforced by the geometry of expanding spacetime. Redshift to zero as photons travel through expanding space. Their wavelength stretches continuously. For photons within the event horizon, this stretching eventually brings them to Earth with heavily redshifted wavelengths, but finite energy. We can, in principle, detect them. For photons beyond the event horizon, the stretching continues indefinitely without the photon ever arriving. What happens to the photon's energy in this case? The redshift parameter Z approaches infinity for photons at the event horizon. Their wavelength stretches without bound. Their frequency approaches zero. Their energy approaches zero. But they never quite reach zero energy. The approach is asymptotic. The photon retains infinitesimal energy even after infinite time. This creates a strange situation where the photon exists, but with energy so close to zero that it is indistinguishable from vacuum. Quantum field theory describes vacuum not as empty space, but as a seething foam of virtual particles constantly appearing and disappearing. The vacuum has energy fluctuations that manifest as temporary particle-antiparticle pairs popping into and out of existence. A photon redshifted to infinitesimal energy has less energy than typical vacuum fluctuations. It contributes less to the electromagnetic field than the random fluctuations that appear and disappear in empty space. At this point, the distinction between photon and vacuum becomes somewhat arbitrary. The information the photon carried has not been transferred anywhere. It has simply been diluted below the noise floor of the vacuum itself. The message still exists, in principle, encoded in the phase and amplitude of an electromagnetic wave with wavelength stretching across cosmic distances. But extracting this information would require measuring the electromagnetic field to precision beyond the limit set by quantum uncertainty. Heisenberg's uncertainty principle forbids perfectly precise measurement of field amplitude and phase simultaneously. The precision achievable in any realistic measurement is far above the signal level of an infinitely redshifted photon. The information is present but fundamentally inaccessible. This is a different kind of information loss than absorption. The photon still exists. Its energy has not been transferred to another particle, but the information has been diluted beyond extractability. In the far future, when all photons have been redshifted to wavelengths comparable to the size of the observable universe, this will be the fate of all electromagnetic radiation. The photons will exist, technically, but they will be indistinguishable from vacuum fluctuations. The universe will have achieved a state where radiation no longer constitutes a meaningful component of its energy content. This is one pathway to heat death, not through absorption and thermalization, but through dilution to irrelevance. The photons never die in the sense of being destroyed. They simply fade below detectability, taking their information with them into inaccessibility. The unobservable universe current cosmological models suggest that the universe extends far beyond what we can observe. The observable universe, the sphere from which light has had time to reach us, has a radius of approximately 46.5 billion light-years. But the universe itself is likely much larger. Inflation theory, the leading paradigm for the universe's earliest moments, suggests that the universe expanded by a factor of at least 10 to the power of 26 during the first 10 to the power of negative 32 seconds after the Big Bang. This would make the total universe vastly larger than the observable portion. How much larger? The answer is uncertain, but some models suggest the full universe could be 10 to the power of 23 times larger in volume than the observable portion. Others suggest it could be infinite in extent. If the universe is infinite, then the observable universe constitutes an infinitesimally small fraction of total reality. Most of the universe is forever beyond observation, hidden behind the horizon created by the finite speed of light and finite age of the cosmos. This unobservable universe is filled with galaxies, stars, and presumably planets. It emits photons constantly. Those photons travel through space, carrying information about their sources, but they can never reach us because they would require more time than the universe's age to cross the distance. These regions are not beyond the cosmological event horizon. They are beyond a more fundamental horizon created by light travel time. Even in a non-expanding universe, we could not see these regions because light from them has not had time to arrive. The information in photons from these regions is not technically destroyed. It simply exists in a portion of space-time that is causally disconnected from our portion. No signal can ever cross between these regions and ours. We are isolated by geometry from most of the universe. This isolation is permanent and absolute. Unlike the event horizon, which could theoretically be reached by traveling fast enough, the light travel time horizon cannot be overcome by any motion. The distance is too great. The time is too long. We are separated from most of reality by barriers of space and time that no technology can breach. The photons emitted in those distant regions carry information that we will never access. They tell stories about galaxies we will never see, stars we will never study, planets we will never know exist. This information exists but is walled off from us by cosmic geometry. And if the universe is infinite, the amount of inaccessible information is literally infinite. For every photon we detect, infinite photons propagate through unreachable regions of space. For every galaxy we observe, infinite galaxies lie beyond observation. Our knowledge of the universe, no matter how it grows, represents an infinitesimal fraction of total cosmic information. Eternal transit for photons beyond the event horizon and photons in the unobservable universe. The journey never ends. They travel at light speed through expanding space, never reaching their destinations, never being absorbed, never interacting with anything except occasional scattering off intervening matter. These photons exist in a state of perpetual transit. From their reference frame, no time passes. Emission and absorption are simultaneous events even if absorption never occurs. But from an external reference frame, these photons travel for trillions of years, then quadrillions, then timescales that exceed any meaningful description. Eventually, even dark matter may decay. Protons may decay, though this has never been observed and may not occur at all. Black holes will evaporate via Hawking radiation. Given enough time, every structure in the universe will disintegrate. But photons do not decay. They have no internal components that could break down. They do not wear out or deteriorate. A photon can propagate for arbitrarily long times without changing its fundamental nature. In the far future, when all matter has decayed or fallen into black holes, and all black holes have evaporated, the universe may contain only photons and dark matter. The photons will be ultra-redshifted, with wavelengths measured in light years or larger. Their energy will be infinitesimal, but they will still exist, propagating through an almost perfectly empty universe. These photons are eternal travelers, journeying through a cosmos that has lost almost all structure and content. They carry information about a universe that no longer exists, stars that burned out trillions of years ago, galaxies that dispersed into diffuse clouds of dark matter. But there is no one to receive the information. No observers remain to detect the photons. No structures exist to absorb them. They simply travel, endlessly, through an expanding void. This is perhaps the loneliest fate imaginable. Not death and dissolution, but eternal existence in isolation. The photons persist, unchanged, while everything else fades away. They become the last remnants of a universe that once teemed with stars and life and complexity. And they carry information that will never be read, stories that will never be told, histories that will never be known. The information exists, encoded in electromagnetic waves spanning cosmic distances, but it exists in a universe where information has become meaningless because there is no one to process it. This is the ultimate fate of photons that escape absorption, not death, but irrelevance. They outlast everything else, only to find that outlasting has no purpose. The journey continues forever, but the destination has ceased to exist. In approximately 10 to the power of 100 years, assuming current cosmological models remain accurate, the last conventional star will burn out. This star, a red dwarf with a mass perhaps 1/10 that of our Sun, will have spent trillions of years slowly converting its hydrogen into helium through nuclear fusion. When the last hydrogen is exhausted, fusion will cease. The star will cool, gradually radiating its remaining thermal energy into space. Over timescales that make the current age of the universe seem like a blink, this dying ember will cool to match the temperature of the surrounding space. The last photon emitted by the last star will be a low-energy infrared or radio wave, carrying barely any energy. It will propagate outward into space at light speed, alone in a universe that has grown dark and cold. This photon will travel through a universe vastly larger than today's cosmos. Expansion will have stretched space to dimensions that trivialize current cosmic distances. Galaxies will have dispersed into isolated dark matter halos separated by voids measuring trillions of light years across. The photon will redshift as it travels. Its wavelength will stretch from centimeters to meters to kilometers to light years. Its energy will drain away into the expanding geometry of space-time. It will become weaker and weaker, fainter and fainter, until it carries less energy than the quantum fluctuations of the vacuum through which it moves. But it will never quite disappear. The energy will approach zero asymptotically, never reaching it. The wavelength will grow without bound, stretching toward infinity but never arriving. The photon will exist in a liminal state, more virtual than real, more mathematical abstraction than physical entity. And there will be nothing to detect it. No observers will remain. No structures will absorb it. It will travel through an incomprehensibly large, cold, dark universe, carrying information about a star that burned out eons ago, destined to travel forever through expanding space. This final photon represents the end of the cosmic story that began with the first photons at recombination. For 10 to the power of 100 years, stars emitted light. Galaxies glowed. The universe was illuminated by electromagnetic radiation carrying information about the structures that emitted it. But that era is finite. It ends when the last star dies. After that, the universe will contain only ultra-redshifted photons from earlier epochs, stretching to longer and longer wavelengths as expansion continues. Eventually, even these photons will have wavelengths exceeding the size of the observable universe. At that point, the concept of photon becomes somewhat meaningless. An electromagnetic wave with wavelength larger than the universe cannot be localized or detected by any structure within the universe. It exists mathematically, but not observationally. The information carried by such photons has been diluted beyond any possible recovery. The message has been stretched so thin across space that it cannot be read. The universe has achieved perfect darkness not because photons have been destroyed, but because they have been rendered undetectable. This is the ultimate fate of light after billions of years of travel. Not a dramatic ending, but asymptotic fading. Not destruction, but irrelevance. The photons persist, technically, but they no longer constitute meaningful components of the universe's energy or information content. The journey that began in violence, in the fusion cores of stars, or the hot plasma of the early universe, ends in silence. The photons continue traveling through expanding space, their wavelengths growing, their energies fading, their information dissolving into the quantum foam of space-time itself. The cosmic amnesia, what does it mean for the universe to forget its own history? The question seems philosophical, perhaps meaningless from a physics perspective. But the progressive loss of information encoded in ancient photons represents a genuine phenomenon with measurable consequences. Every year that passes, some fraction of the cosmic microwave background photons are absorbed by dust, gas, or detectors. These photons carried information about the surface of last scattering, about density fluctuations in the early universe, about conditions 380,000 years after the Big Bang. Once absorbed, that specific information is lost. Other CMB photons carry similar information, providing redundancy, but the total information content gradually decreases. Simultaneously, cosmic expansion continues redshifting the remaining CMB photons. Each year, their wavelengths stretch slightly longer. Their energies decrease slightly. The signal-to-noise ratio for detecting temperature fluctuations degrades slightly. The information becomes slightly harder to extract. On human timescales, these effects are negligible. The CMB will remain detectable for trillions of years. But on cosmic timescales, the trend is clear and irreversible. Eventually, the last CMB photon capable of being detected will arrive. After that, no future civilization will be able to study the background. That entire window into cosmic history will have closed. The same process affects all ancient light. Photons from the first galaxies, carrying information about star formation in the early universe, are being absorbed and redshifted out of detectability. Photons from distant quasars, revealing conditions billions of years ago, face the same fate. Every category of ancient light is subject to this double assault of absorption and redshift. The universe is systematically erasing the evidence of its own past, not through any intentional process, but through the inevitable operation of expansion and thermodynamics. Information leaks away continuously, irreversibly, until nothing remains but the present moment and whatever records observers managed to preserve before the information was lost. We are extraordinarily fortunate to exist at a cosmic epoch where so much ancient light remains accessible. A trillion years hence, future cosmologists will have access to far less information about cosmic history. They will not be able to measure the CMB. They will not be able to observe the most distant galaxies. They will not be able to study the early universe through direct observation of ancient photons. Their understanding of cosmology will be based primarily on theoretical models and whatever observational records their ancestors preserved. They will live in a darker universe not because fewer stars shine, but because the light from distant cosmic epochs will have faded beyond detection, and their descendants, trillions of years later still, will inherit an even darker cosmos. The progressive loss of information is inexorable. Each generation loses access to evidence that earlier generations could observe. The universe becomes increasingly mysterious as the messengers from its past are silenced by absorption or diluted by expansion. This amnesia represents one of the most profound facts about our universe. We live in a temporary window of observability. Before this window opened, the universe was opaque and photons could not travel freely. After this window closes, expansion will have carried most of the universe beyond observational reach, and ancient photons will have faded into undetectability. We are reading the cosmic story while the book remains open. Future generations will find only scattered pages. Eventually, the entire text will have been erased by time and geometry. Conclusion: the message in Dying Light does not last forever. Information does not persist eternally. The universe does not preserve memory. Every photon is a message written in disappearing ink across expanding paper. We are lucky to read any of them before the ink fades completely. This is not tragedy. This is thermodynamics. The photons that began their journey billions of years ago, carrying information about stellar births and galactic formations and cosmic dawn, arrive at our telescopes damaged by their passage through space and time. They have been redshifted by expansion, scattered by dust, bent by gravity, drained of energy by the geometry of space-time itself. Yet they still carry information. Degraded, incomplete, statistical rather than precise, but real. We can decode their messages. We can reconstruct the history they tell. We can learn about the universe's first billion years, about the formation of structure, about the evolution of cosmic chemistry. But we can only do this because we exist now, in this brief cosmic moment when the information remains accessible. The window is closing. Every second, photons complete their billion-year journeys and are absorbed, their information extracted and preserved or lost forever. Every second, more photons cross beyond the event horizon, joining the population of dark messengers that will never deliver their messages. The universe is teaching us a lesson about the impermanence of information. Physical structures decay, memories fade, records crumble, and on the longest timescales, even light itself, the fastest messenger, the most fundamental information carrier, succumbs to entropy and expansion. What does this mean for us, for humanity, for any civilization that arises in this cosmos? It means that knowledge is temporary. Understanding is ephemeral. The scientific edifice we build through observation of ancient light rests on a foundation that is actively eroding beneath us. Not in our lifetimes, not in a million years, but eventually, inevitably, the information accessible to observers will be less than what we can access today. The universe will have forgotten more of its own history. The cosmic archive will have lost more pages. This creates an imperative, if anything can be called imperative in a universe that operates without purpose. Observe now. Measure while measurement is possible. Record before the information is lost. Extract knowledge from ancient photons while those photons still carry enough energy to be detected. Every CMB measurement we make preserves information about the early universe that will eventually be lost to expansion. Every observation of distant galaxies captures light that future observers will never see. Every photon we detect is one of the last messengers from cosmic distances that will soon fall beyond observability. We are living witnesses to cosmic history, not by choice, but by accident of existing at the right epoch. We did not earn this privilege. We merely happen to exist when the universe remains transparent enough to reveal its past. But having this privilege, We carry a responsibility to those who come after, to observe carefully, to record thoroughly, to preserve what we learn. Because the original sources, the photons themselves, will not be available to future generations. They will have only our records, our measurements, our interpretations. In this sense, astronomy is not just science, but archaeology of the most literal kind. We are excavating the past before it erodes completely. We are reading ancient texts before they fade into illegibility. We are preserving memories before the universe forgets. Epilogue. Reading while you are reading this because photons reached your eyes or your screen. Those photons traveled from their source, perhaps an LED in your monitor or sunlight reflected from paper. Their journey measured nanoseconds or microseconds, trivial compared to the cosmic odysseys described here. But even these mundane photons follow the same physics. They too redshift, though by amounts too small to measure. They too carry information that will be lost when they are absorbed. They too contribute to the heat death of the universe, transferring ordered energy into disordered thermal motion. The difference is one of scale, not principle. The photons bringing you this text traveled meters or centimeters. CMB photons traveled 13.8 billion light years. But both face the same fate: absorption, energy transfer, information death. Every time you see anything, photons die. Every measurement destroys photons. Every observation converts electromagnetic energy into heat and neural signals. We live by killing light. But we are living in a privileged era. The CMB is still detectable. Distant galaxies still shine. The universe still offers windows into its history through photons that have survived their billion-year journeys. In the far future, these windows will close. The light will fade. The information will be lost. Future observers, if any exist, will inherit a darker universe with less accessible history. We are the generation that can still read the message. Every night, ancient photons arrive from the depths of space and time, carrying information about cosmic dawn, the first stars, the assembly of galaxies. Every day, astronomers collect these photons, decode their information, and reconstruct the history they tell. This work is urgent not on human timescales, but on cosmic ones. Every million years, some photons complete their final journey from regions falling beyond the event horizon. Every billion years, the CMB fades a little further. Every trillion years, more information becomes inaccessible. Eventually, the last photon from the surface of last scattering will arrive. The last photon from the first galaxies will be absorbed. The last photon from the distant quasars will fade below detectability, and the universe will have forgotten its youth. We are reading the cosmic story while we still can. We are measuring the photons before expansion dilutes them into irrelevance. We are the universe becoming conscious of its own history, using the dying light of ancient photons to illuminate the past. The photons have traveled for billions of years. They have survived redshift, dust, gravitational lensing, and countless other hazards. They have carried their information across cosmic voids to arrive at our telescopes. And now we measure them. We convert their electromagnetic energy into data. We analyze their spectra. We decode their information. We tell their stories. Then they are gone. The photons that traveled 13.8 billion years are destroyed in femtoseconds of detector interaction. Their infinite journey ends in an instant. The information is preserved in digital form, but the photons themselves cease to exist. This is what happens to light after traveling for billions of years. It arrives, it is measured, it dies, and in that death, it tells us about the universe. The stars that emitted the photons we detect tonight might no longer exist. They may have exhausted their fuel and collapsed billions of years ago. The galaxies that sent us light might have merged with neighbors or been torn apart by tidal forces. The cosmic structures we observe are ghosts, images of things that were, not things that are. But the photons are real. They exist now, in this moment, carrying information from that distant past into our present. They bridge the gap between then and now, between there and here. They are time travelers that experience no time, connecting events separated by billions of years in a single quantum thread. When we detect these photons, we are not merely measuring light. We are making contact with the past. We are reading messages sent before Earth existed, before our sun formed, before our galaxy took its current shape. We are receiving transmissions from a cosmos utterly alien to our present epoch, and we are among the last who will be able to do so. The inexorable march of cosmic expansion ensures that future observers will have access to less and less of this ancient light. We occupy a narrow window in cosmic history where the universe reveals its secrets to those who know how to look. So we look. We build larger telescopes. We design more sensitive detectors. We develop better analysis techniques. We extract every bit of information we can from the ancient photons that complete their journeys in our era. Because we know that these photons are dying, not just individually, when they strike our detectors, but collectively, as a source of cosmic information. Every year, the light from some distant galaxy crosses beyond the event horizon for the last time. Every year, the cosmic microwave background fades imperceptibly. Every year, the universe forgets a little more of its own story. We are racing against cosmic entropy, against expansion, against thermodynamics itself. Not to win. The universe will eventually forget regardless of our efforts, but to document, to record, to preserve what we can before the original sources fade beyond recovery. This is why astronomy matters, not just as science, but as the last chance to read the universe's autobiography before the pages crumble into dust, not just to satisfy curiosity, but to preserve knowledge that will never be accessible again once the light fades. The photons keep arriving, and we keep watching them die. Each one tells us something about where it came from, what it encountered along the way, how the universe has evolved since it began its journey. Each one adds to our understanding of cosmic history, and each one that dies is one fewer photon carrying that information, one fewer messenger from the ancient cosmos, one fewer opportunity to learn about the universe as it was. This is what happens to light after traveling for billions of years. It finds us, briefly, in the darkness. It whispers its secrets before dying, and we listen, while we still can, before the universe falls silent. The last photon has not yet arrived. The final message has not yet been delivered. The cosmic archive is still being written, one dying photon at a time. But the ending is already determined. It is written in the equations of general relativity and thermodynamics. It is enforced by cosmic expansion and quantum mechanics. Eventually, the photons will stop arriving, not because stars stop shining, though eventually they will, but because expansion will have carried their sources beyond the cosmological event horizon. The light will still be emitted, but it will never reach us. When the last detectable photon from the cosmic microwave background arrives and dies, a door will close forever. Future civilizations will never be able to study the CMB directly. They will have only our records, our measurements, our theories. And those records will themselves decay over geological time. Digital storage degrades. Physical media crumbles. Civilizations fall on timescales of millions or billions of years. Even our most carefully preserved knowledge may be lost. The universe forgets, and we, temporary custodians of cosmic knowledge, can only delay the inevitable. We cannot prevent it. We cannot stop expansion. We cannot halt entropy. We cannot make photons immortal. But we can observe. We can measure. We can understand. We can tell the stories that dying photons whisper to us in their final moments. This is our privilege and our burden, to be the generation that witnesses cosmic history through ancient light, to preserve what we can before the light fades, to understand that we are reading a book that is actively being erased, page by page, word by word, letter by letter. The photons keep arriving. Each one has traveled farther and endured more than any human journey. Each one carries information more ancient than our entire planet. Each one dies to deliver its message, and we receive that message. We decode it. We add it to the vast mosaic of cosmic understanding that humanity has been assembling since we first looked up at the night sky and wondered. This is what happens to light after traveling for billions of years. It reaches us. It teaches us. It dies. And in doing so, it makes us witnesses to the grandest story ever told, the story of the universe itself, told in the dying whispers of ancient light. The journey ends. The photon dies. The information is preserved or lost. And somewhere in the depths of space, another photon begins its own billion-year journey toward an unknown destination, carrying information about a cosmos that will have changed beyond recognition by the time the message arrives. If it arrives at all,